Now, note there's been a little bit of sleight of hand here. And the sleight of hand is that I've been mostly talking about data correctness. But when we talk about correctness from the perspective of things like PEP 484 or from the perspective of things like unit test, we're typically talking about code correctness. Now, we all know that there is a spectrum from data to structure, from data to code. And in some programming languages like Lisp, the distinction is harder for us to observe. Things that we might call data in Python might appear as code in another language. These may be homoiconic languages where data and code look very similar to each other. But as Python programmers, and since our examples are formulated in Python, we usually have a fairly strict formulation whereby some things are clearly data and some things are clearly code. When we talk about code correctness, typically what we're talking about is not that we created data entities, but that subsequent actions that we performed on those data entities were then correct. So, for example, we have this class here, and it has this method. This method returns some sort of integer value. It takes no arguments. This integer value has an operation performed on it, and we're trying to assess are the subsequent operations going to be correct or not. And this is typically what we mean by code correctness. You can see this is closely related to the data correctness. Obviously, if the data is wrong, the subsequent code operating on it has certain, especially in a dynamic language like Python, has certain effects whereby, x plus y could be an integer value if x and y are both integer values. But if one of these is no longer integer value, if they're both string values, this is no longer correct. So you can see there is an interplay and an interrelationship here. Typically, when we talk about code correctness, we're also talking a couple of levels of abstraction higher. So we're talking about not just, is the code here that call data model method correct, but is the class itself correct? And are there certain guarantees that we might put on the class? And when we talk about the more advanced features of Python, specifically features like class decorators, metaclass, and its subclass, we're often talking about a fairly high level of abstraction for the code correctness. But ultimately, we can usually boil everything down to a notion of data correctness. It's just very difficult for us to work with in Python, since Python tends to maintain a stricter distinction here. Also, note, one important characteristic when we're talking about correctness is whether we're talking about statically checking this correctness and dynamically checking this correctness. And you can see the words static and dynamic, they're very overloaded. They're used to reference a lot of different things. Typically, when we say static, we mean one point in time. When we say dynamic, we mean might change over points in time. When we talk about the time when something is checked, we typically mean, is this checked prior to the deployment environment where the code runs, or is this checked in the deployment environment where the code runs? And a very simple example is, here we have a function of 2 arguments. This code is strictly incorrect. It only passes 1 argument in. That argument y is not optional. However, if we run this code, we will not see an error until this line runs. This is why we might need something like PEP 484 tools like MyPy or Pyre in order to check this ahead of time, because this might not be 1 second, but might be 100 seconds. It might be the case that this is 100 seconds at some probability of whether we actually reach this point in the code. And all of that really reduces our ability to say, oh, this code is guaranteed to be correct. Well, in programming languages like C and C++, we put a lot of work onto the compiler. And as a consequence, we say if it compiles, that gives us a notion of the correctness of this code. But as you know, the Python compiler is actually a very small thing. It doesn't really do a whole lot. In fact, I would say it probably does 3 or 4 interesting things in total. There is a compiler in Python. The compiler in Python is what takes our source text and turns it into bytecode. And if you want to see the Python compiler at work, just use the dis module. And you can see here the Python compiler took this function and it turned it into these bytecodes. We can even take a look at what the bytecode is by looking at the code here. That's what the Python compiler does. Now, it doesn't compile it into machine code, and it's not really what we'd call a compiler in the sense of, say, C or C++, since it generates this bytecode, and there are some material differences, but it's still a compiler. It does translate one thing from another into another thing. The Python compiler does do some work. The Python compiler will, for example, determine things like the scope of a variable. So it'll determine whether it wants to emit a different bytecode. For example, a load fast or a load global, or if it's the case that this is a dereferenced closure variable, a load deref. Let's give this 2 arguments. See a load deref there. So the Python compiler does that. The Python compiler can subsequently also check for name errors. It's not something that people typically use the compiler for, but it can tell, you can, for example, annotate this code and say, look, I'm looking for a name Z. Since you're already looking for where this thing is located in order to determine what the scope is, in order to give the correct load operation, just make sure they don't have any typos. So the Python compiler could actually do some very simple things like check for typos in variable names, not in attribute lookups, because the Python compiler considers all attribute lookups to be identical. So if we do something like this, it can't really tell that this is, one attribute or another. And there could be a get attr and get attribute mechanism. So that's quite limited. But in terms of the actual variable, it can determine whether that variable exists or not. So here, if I accidentally type the Z, you can see there's a load global here. And if I didn't anticipate a load global here, I could flag that error. In addition to that, the Python compiler also does name mangling within class bodies. And it also does the I don't know if you call it super mangling, but it handles the argumentless super and fills in the remainder arguments. So it doesn't really do a whole lot. When we conceptualize how we might think about Python code in relation to C, C++, or Java code, in C, C++, or Java code, or even other programming languages, we have a compile step and then the run step. I would say the closest equivalent in Python would be not just the compile step, but remember, this is dynamic code. So if I do something like this is completely valid. This is live running code. There really isn't that distinction of we compiled and then we ran. It's really that as we were running the code, it did some work. But at the same time, we typically don't see very messy things happening at the module scope. So in general, what I would talk about is if we want a static view of is my code correct in Python, the closest we can usually get, and reasonably close place that we can get, is module import time. Can we add checks at the module body such that when you import the module, it checks to make sure things are correct? And if you think about it, that's actually pretty reasonable to do, because before you deploy your code to production, you could just sit at your console and just import every module. And if the modules import, that could give you a sense of correctness. Maybe not as strong a sense of correctness as what you might get from a very powerful compiler like the Rust compiler, but could give you some notion of correctness. Let us talk about a correctness mechanism, specifically a mechanism for determining the correctness of some data. Let's talk about the property decorator in Python. Let's take a look. Here, we have a data class, and this data class has some subordinate data. That is to say, you pass it 1, 2, 3, 4, 5, 6 as the values x and y, and it computes from that the value z. And I've marked this as frozen so that if I look at .z, well, .z is going to be x plus y. Okay, that looks correct. And I can't actually change what x is in order to make this invalid, in order to make that z no longer the addition of x and y. Now, you could say that this might be something that is a little bit more descriptive. That's why I call it z. That's why in my code I don't want to repeatedly write obj.x plus obj.y, or you can imagine that this computation might be a little bit more complicated, and it might be the case where this computation really should lie very close to this class. That may be why I have this third entity that's wholly determined by these other two entities. Note that if I added this as a field onto this data class, this would give me the ability to see it here, which may or may not have some benefits. You can see it in the repr, so that may or may not have some benefits for my end users to know that this is there. Whatever the case may be, you can see that the post init is using this object set attr pattern in order to set this z, and by virtue of this thing being frozen, I can't change it later. However, while this is an immutable piece of data, it is the case that data does change. And as a consequence, there may be the case where this T evolves over time. This entity evolves over time. So what might I do in order to evolve this entity over time? Well, thankfully, data classes include a replace method, which allows you to replace fields. And so here, you can see that I have my object with x and y, where I have changed the value of x from 123 to 123,000. And when I use this replace function, note that it reruns the post in it. So thankfully, the correctness of this data is maintained. And so one thing that I might do in my code is I might say, you know what? I have my data class. I'll always use frozen data classes. But if I need to represent that this thing evolves over time, for example, there's a correction made to this data, or just some data naturally represents something that is not a point in time, but some kind of moving value, well, I'll just do a replace operation and I'll swap this out. Note one other really cute thing about this replace is this replace only replaces the one field. So if x and y are very rich objects, very large objects, well, if those subsequent pieces are themselves immutable, so for example, this is some large object A, and this has a lot of fields in it, well, the nice thing is, if I'm swapping out y, I'll actually just have a reference to a. And so I'll have this large graph of each instance of t over time, referencing each instance of a with the value of that. I'll deduplicate effectively what this data looks like. So it's quite nice because I won't use any additional memory. If the a values are, if the x values are the same, this large a object will only be stored once, and only the things that have changed will be swapped out. So if I do that with enough granularity, I might even end up not really using a lot of additional memory for objects that change quite a bit, and still give the ability for me to track the entire history of the evolution of these data members. But it is the case that in certain circumstances, we want mutability. Now, in all honesty, I'm not that swayed by the argument that we want mutability because fundamentally things in the real world are mutable. I'm not that swayed by it in part because we're talking about a computer program here, and in a computer program we're talking about a simplification of reality, and so necessarily we're talking about, making things easier for us to manipulate. And in that case, if we deal with only immutable data and all we do is use that replace method, well, we do store more data. I actually buy the argument that immutability will probably lead to more storage requirements than mutability. I buy that a little bit more. But it's the case that we could throw away old data if we wanted to, and if we work with only immutable data, then it's probably the case that we implicitly get the entire history of the data, which makes debugging easier, makes certain types of reporting much easier, because we can see the entire history of how something has changed in your program. However, one reason why we might want mutability in our program is also a reason why we might not want mutability in our program, specifically action at a distance in the absence of an established API. Let me show you an example. In our Python Advanced class, we show examples like this all the time. We ask people if they can distinguish between these four implementations of this simple class. And note, the difference in these four implementations are just in their inits. So their repers all look the same. Here, in the first init, I'm just passing in some arguments to this class. In the second init, I'm passing those in using argument unpacking. In the third version, I'm making a copy using the .copy method, or I could, of course, use the copy module. And in the last version, I'm using this extended unpacking. And each one of these are subtly different. Obviously, it is the case that these three will copy the container. So this one is a live view of the container. So for example, if I don't pass in the arguments in the way that I did down here, but I instead instantiate them and then pass them in, and then later make a change to this is what I mean action at a distance, well, in the first case, you would see that difference. In the last three cases, you wouldn't see that difference. And so, oh, okay, there actually is something of difference here. Of course, in this case, here the syntax is very slightly different. You'd have to do an unpacking in the call. But outside of that syntactical difference, in these last three cases, you wouldn't see that action at a distance because you're making a copy or taking a snapshot of this data. In the first case, you would. Now, in the last three cases, there are other slight differences. For example, here, the args are a strict list. Whereas here, this is whatever type you passed in, and this here is a strict tuple. So you can think that in the middle of these three copied cases, if this isn't a Python list, but a collections.dec, well, here, args will be a collections.dec with the behavior pulled through, even if the data has been copied. Whereas in these two cases, you no longer have availability of that behavior, that collections.dec behavior, like the pop left or the append left. You only have whatever behavior is available on, of course, a strict tuple or on a strict list. But in the case of this first one, well, you have exactly that same data with exactly the same behaviors of whatever type that data has. And of course, as long as you just mandate that this thing has the properties of a sequence that you can iterate over, you can append it and things like that, some kind of mutable sequence, then all of your code will work. Here, you can see the idea of action at a distance. You may specifically choose version 1. This may be necessary so that people can change the data and that change is visible at some distance. You may also specifically choose one of the latter three because you might say, that's going to get really confusing because somebody writing this line of code may not expect the object to change, in which case they're going to get very confused. So you can see an argument for and against this idea of mutable data and having live views of that mutable data. Now note, if you have immutable data and you want somebody on the outside after the construction of this data to be able to change the inside, well, you have to create an API for this. So what you'd have to do is you'd have to do some kind of API here. So here, something like this. And I guess here you could do the same thing. Here, you can still mutate the internal details of this class. You just have to go through an established API. Well, think about this. The reason that we might want to have action at a distance in the absence of an established API is that if we have to establish an API to change the internals of this class, we have to know what that API looks like, which means we have to constrain ourselves to some knowledge of what the internal representation of these args might look like and what operations we're allowing to be performed on this thing. And as a consequence, that means we're making a lot of presumptions up front, which reduce the flexibility of our code. One of the reasons that we might want action at a distance in the absence of an established API is we might want to say, look, by doing that, I'm really limiting the flexibility of my code. I'm really limiting the ability for somebody to add something to this code or for somebody to do some operation on this line here that I didn't anticipate and I didn't write an API for, but the code still works. And I'm just going to trust that if you do that knowledgeably, you do that purposefully, you do that knowing what the consequences of that will be. And so this is why we might want mutability. We may want to provide external users the ability to inject some behavior and to make changes on the internal details without us having to affirmatively determine upfront what an API is for doing those operations. Now, do note that when we use things like coroutines or generators, it is the case that generators and generator coroutines are fundamentally mutable. We can step through them forward, as are many types of different iterators. And as a consequence, you can think that that pattern is somewhere in the middle between these two ideas. That is, if you pass in a generator or a generator coroutine to a class, you are allowing somebody externally to mutate that generator coroutine by stepping through it, but they're doing it in a very constrained fashion, even though this class doesn't have an established API. The generator coroutine have an established API, and that established API is you can basically do a next or a send, and that's it.